Hello, everyone. Welcome to our webinar titled Lanthanum BromoChloride, a deep dive into scintillator innovations. My name is Alan, and I'm the Vice President at Berkeley Nucleonics. It's a pleasure to have you all here today. Let's dive right in with an introduction to scintillators and their pivotal role in radiation detection. Scintillators are materials that emit light when they absorb ionizing radiation. This unique property makes them incredibly valuable in detecting and measuring radiation across a variety of applications. So, the concept of scintillation has actually a rich historical context. The discovery dates back to the early 20th century with significant advancements made during the Manhattan Project. So, since then, scintillation technology has evolved tremendously. We've moved from rudimentary scintillators like zinc sulfide to advanced compounds such as lanthanum bromochloride, which we will discuss in detail today. So, these advancements have enabled us to deploy scintillators in very critical applications like medical imaging. They're used in PET and CT scans to provide high resolution images. Even in environmental monitoring, scintillators help detect and measure radioactive contamination. So they're also critical in security, enabling uh, detection of illicit radioactive material. So there's a lot. Additionally, in scientific research, scintillators are used in high energy physics experiments to explore fundamental particles and forces. So the significance of scintillators in these industries cannot be overstated. Their ability to convert radiation into visible light with high efficiency and accuracy makes them indispensable tools in radiation detection and measurement. So, why are we here today? Our goal is to explore the latest innovations in scintillator technology with a particular focus on lanthanum bromochloride. So, we'll discuss its unique properties, advantages over traditional scintillators, and the potential it holds for future applications. Every year we attend conferences like the IEEE Nuclear Symposium, and we hear about the next big scintillator and detector that will change the game. However, we want to ensure that we do our due diligence before we start offering and using new crystals. But before we kick things off, I want to give a big shout out to our European partners at Psionics. Thanks to their support and expertise, we've made great strides here in the US and around the world. For those that don't know, in Netherlands, they have been producing scintillation detectors since the 1960s. And it takes a ton of know how to get them just right. So, Psionics, founded in 1992, has built on that rich history to become a top player in the field. So, a big thank you to you, Psionics. Uh, we're going to get this presentation started. Again, it will be myself and it will be my colleague, Mark Slattery. He has a ton of knowledge in this industry. He talks to universities, laboratories, private, the public sector. So you're going to get a chance to ask him questions towards the end of the presentation, but he'll be giving you more insight into this very, very unique and very promising LBC crystal and detector. So, question. We're trying to get feedback from everyone here. We want to make sure that we're all have a good understanding of of what crystals are used. So, First question, what type of scintillation detector are you most interested in? Is it LBC? Is it, or are you just here because you want to see how it compares to cerium bromide, to sodium iodide, how it compares to lanthanum bromide? As of right now, what type of scintillation detector are you most interested in? Okay, so now I'm going to pass it off to my colleague, Mark Slattery.
Hi, I'm Mark Slattery, Nuclear Applications Manager at Berkeley Nucleonics, and for over 15 years. And let's talk about the science of scintillation. Now, we're not speaking of radiation detectors like gas-based ion chambers or solid-state semiconductors, that kind of thing. A scintillator is material that, when exposed to ionizing radiation, it converts the absorbed energy into pulses of light. The ionizing radiation is in the form of X-rays, gamma rays, and particles such as alpha, beta, neutron, and so forth. The energy ranges from a few thousand electron volts to millions of electron volts. And then light detectors like photomultiplier tubes, silicon photomultipliers, and photodiodes. They're then used to convert the pulses into electrical charges and then further convert the charges to measurable voltage signals for electronic instruments to measure and analyze the output from the scintillator. Organic scintillators are typically made of plastics and liquids that are doped with scintillating organic molecules. Plastics are typically low-density materials that are well suited for particle detection of alphas and betas, which don't penetrate very deeply. And they're also well suited when very large volume scintillators are required in an application. That's because the plastic materials are relatively low cost. Liquids are denser than plastics. They're better suited for neutron detection, which penetrate much more deeply. Inorganic scintillators are largely the result of growing crystals, glass, and ceramics. These are man-made constructions of molecular chains, and that's why they're called inorganic. They're unnatural. When thallium doping of sodium iodide occurred in 1948, the result was a material that scintillated with a light bright enough to eventually be converted to electrical signals. And this had a huge impact on the science of scintillation. This led to the advancement of spectroscopy. Almost immediately, the challenge was to create inorganic scintillators for high energy physics, particle physics, astrophysics, and they needed to be faster, brighter, and denser than sodium iodide. And then, borrowing from the Olympic motto, I like to think of it as Sidious Lucidus Gravius, faster, brighter, and denser. And I mean that in a good way. Driven by interests for increased security measures around the world, the research focused primarily on greater energy resolution using 662 keV gamma energy as the touchstone. This led to the discovery and development of proportional materials. Tremendous energy has been focused on materials like lanthanum halides, cerium bromide, strontium iodide, cesium, lithium, yttrium chloride, better known as CLIC, cesium, lanthanum, lithium bromochloride, also known as CLLBC, and gadolinium, aluminum, gallium, garnet. I'm glad we call it GAG. Anyway, lanthanum BromoChloride was first introduced in 2006. It's a variation on the well-established and better-known scintillator, lanthanum bromide. LBC possesses an enhanced mechanical strength over lanthanum bromide. It's also more rugged than cerium bromide or sodium iodide. It makes it better suited for demanding, say, outdoor applications, including field operations, outdoor environmental monitoring, and site remediation. As with lanthanum bromide, LBC also contains the same intrinsic background from the isotope lanthanum-138. It can be an issue for low background applications, but on the other hand, those known energies can also be used as calibration energies. And that can eliminate the need for seed sources in some detector systems. So, what defines a better scintillator? It depends entirely on the application. We'll talk more about that as we continue.
Next question. What features are most important to you in a scintillation detector? So is it the size? Is it the resolution? Is it the cost? Is it the ability to be durable? Is it the acquisition time? Is it the PMT that you're using? So again, this question uh, will definitely will help you really determine what detector you're going to be focusing on. Again, the common ones are sodium iodide and cesium iodide. But again, what features are most important to you in a scintillation detector? This is a gamma spectroscopy and resolution. So again, include that answer in this poll.
Okay, we're back. Let's talk about the properties and benefits of lanthanum bromochloride. Brightness in a scintillation material is technically referred to as light yield or photon yield. And that is how much light is emitted, visible light, when exposed to radioactivity. LBC generates 75,000 photons of ultraviolet light for each MeV of gamma energy that it absorbs. And that means even for low gamma energies, you can still get a very measurable optical light. So 75,000 photons per MeV is the light yield. That's very bright. In fact, I think it's about the brightest that we're able to provide. Decay time is like this. The photons of optical light flash when the scintillator absorbs gamma photon. And then some time has to pass for the bright flash to dim and decay so that measurable photons of optical light can flash again when another gamma photon is absorbed. So this span of time at which the light dims sufficiently to flash again is often referred to as the speed of the material. But what does that mean? At less than 25 nanoseconds, lanthanum bromide has very short decay time. It is among the fastest scintillators, and that's without any accompanying slow optical components that sometimes can follow along with some materials. This is very important for processing high volumes of radiation or photons in applications and in applications where timing is essential. So decay time, less than 25 nanoseconds, will say that lanthanum bromochloride is fast. And then besides being bright, a LBC is also very dense. And I mean that in a good way. Density helps determine how well a material can absorb gamma photon energy. The more density, the better absorption of gamma energy, so more scintillation lines generated with greater efficiency. For extremely high gamma energies, over 1 MeV or so, the effective atomic number of the material, that's referred to usually as Z, well, the high Z of LBC is 44.5 That's pretty high. And that property minimizes pair production. So 5 grams per cubic centimeter, and effectively, an effectiveness of 44.5. Excellent absorption for high energy. Now for LBC, the optical light, output of the light is proportional to the gamma energy that it absorbs. This proportionality of the output light across the gamma energy range is critical for generating, well, very predictable and cohesive pulses relative to the gamma energy. This is how one can distinguish the difference between the gamma energy measured at a particular value of kiloelectron volt from a closely spaced energy at a higher or lower value of keV, and it's referred to as energy resolution. At 662 keV, full width, half max, 2.8% variance from the center peak is exceptional. And again, this is primarily a function of the proportionality of the crystal material. We'll discuss that in a little greater detail as we go on. Energy resolution at 662 keV, 2.8%, we'll call that excellent. The optical pulses that are emitted by the absorption of gamma energies have to be at a detectable wavelength. Now, 380 nanometers is in the ultraviolet range, barely, and it's in the visible light spectrum, ultraviolet visible light border, really, and making it well suited for bialkali photomultipliers and silicon photomultipliers. Again, it's extremely proportional across the energy spectrum. For practical purposes, a scintillator has to be produced in amounts and dimensions on an industrial scale. And so along with that, of course, as we get to larger sizes, we don't want any degradation in the material or the quality for the larger sizes. LBC is commercially available up to 51 millimeters, call it 2 inches, up to lengths. Let's see, the 2 inches, I'm referring to diameter, up to 102 millimeters long, 4 inches. That's commercially available for LBC. Given those numbers, square shapes, should they be needed, are then limited to like 36 millimeters by 36 millimeters. CEE and ESA evaluations are ongoing. I don't have a specific value to offer, but LBC is widely considered to be radiation hard. Generally, the radiation hardness is excellent. Now, LBC generates 28% more signal than sodium iodide, and it's 10 times faster. So higher count rates are possible. Co-doped lanthanum bromide, for which the patent has recently expired, originally, ideally, it has a energy resolution of 2.4%, but that's really hardly ever achieved. The 2.4% is sometimes published as 2% by rounding down, but for all practical purposes, LBC has the same resolution at full width, half max amplitude for 662 keV as lanthanum bromide. Namely, we'll call it 2.8%. As I mentioned earlier, LBC is affected by the same internal contamination from lanthanum-138, which is responsible for a significant background near 32 keV, continuing on up to around the 1461 keV region of naturally occurring potassium-40. Another region of background begins at about 1.5 MeV through 2.8 MeV. And again, it can be a blessing as well as a curse depending on the application. The background activity is 40 picoseconds per cubic centimeter. It's about 1.5 becquerel per cubic centimeter. Also, the cost is comparable to cerium bromide and lanthanum bromide, That is to say that it fits between the two other scintillators in terms of cost. And LBC is hygroscopic, so it has to be encapsulated to protect against the absorption of moisture. It's got to be handled in dry boxes if it's not encapsulated, and these are often filled with argon gas, handled with like rubber gloves and so forth. Continuing with energy resolution, it's determined by a combination of these functions: non-proportionality, photoelectron statistics, light collection uniformity, and PMT effects also affects the light collection uniformity. Well, the photon non-proportional response, NPR, the NPR for LBC at 32.2 keV is 95.3% compared to, say, 89.2 for cerium bromide. LBC is more proportional than cerium bromide. The proportionality of a scintillator means that the output pulse is proportional to the energy deposited in the scintillator, as we mentioned earlier. Increased proportionality means better energy resolution. I'd like to point out that there is more research still to be done and advances to be made. And BNC is fortunate to partner with Psionics Holland. They have achieved key results in research that is spurring future development. Intrinsic background radiation from lanthanum 138 is, well, it's impossible to eliminate, but methods are being explored to reduce alpha background in the spectra of LBC. Also, there's ongoing research to evaluate the effect of co-doping. That's by doping the scintillator, we can change aspects of the material, such as changing the crystal structure, changing aspects of performance, like increasing the energy resolution. There are surprisingly few published papers on LBC, but I have included some here on this particular slide. Medical imaging uses scintillation crystals to detect radiation. Radioactive tracers are injected into living bodies, and the scintillators are used to produce images of organs and tissues inside the body or the organism. It's a powerful diagnostic tool that helps physicians observe the movement and concentration of radiation within the living tissue to detect and diagnose diseases. Often, BGO and LISO have been used because they're both quite dense and they have relatively low intrinsic background radiation. LISO has the added benefit of being quite fast so that high count rates can be more easily processed. However, both materials are not particularly bright, and I don't mean that in a bad way. Both have rather poor to middling energy resolution. Though not quite as dense as those two materials, LBC still has considerable density and stopping power, and LBC is far and away brighter and faster with top of the chart energy resolution. I was going to say off the chart, energy resolution as well. LBC has drawn considerable interest and earned extensive ongoing research for this application. Besides imaging, LBC is also gaining traction in health physics in general, things like monitoring contamination, so forth. LBC is also used in gamma ray imaging instruments for plasma physics, also applied for particle accelerators as well. LBC is already being used in CubeSat missions because of its fast decay time and superior energy resolution. Inspections of cargo containers, that requires ruggedness, and this is particularly useful in monitoring and making sure that there is compliance to the nuclear non-proliferation agreements for special nuclear materials. LBC has improved mechanical strength for such operations. It's mechanically stronger than lanthanum bromide. The enhanced mechanical strength and high resolution capabilities of LBC make it particularly useful not only in safe environments where lanthanum bromide is used, but more suitable for more demanding settings that require mobility. It makes LBC an ideal choice in field operations involving outdoor environmental monitoring. We've mentioned that, where the equipment may be exposed to mechanical stress. BNC offers LBC as an optional detector in all of our radioisotope identifiers. On this slide, I've also listed some of our current customers that are achieving excellent results with LBC in their applications. Auburn University, the Korea Research Institute, Los Alamos National Laboratory, Naval Information Warfare Center, and NASA Goddard Space Flight Center. And then Texas A&M University, I always want to say TAMU, Texas A&M University, University of Michigan, and University of Tennessee. Interest is still growing, and I expect to see that list growing as well.
Over the past few years, there's been a significant research and development in lanthanum bromochloride. One of the most notable advancements is the enhancement of its light yield and energy resolution. So researchers have optimized the crystal growth process, which has resulted in scintillators that provide high resolution images and more precise radiation detection. So this improvement is crucial for applications requiring high accuracy, such as medical imaging and homeland security, where every detail matters. Beyond performance benefits, we've seen remarkable progress in integrating LBC scintillators with cutting edge readout technologies. So, for example, the combination of LBC with silicon photomultipliers, SIPMs, has shown great promise. SIPMs offer higher sensitivity and faster response times compared to some of the traditional photomultiplier tubes, so making detection systems not only more efficient, but also a bit more compact and versatile. So this integration opens up possibilities for portable and field deployable radiation detection solutions. So looking ahead, several emerging technologies and future trends could further revolutionize the use of LBC scintillators. One such trend is the development of hybrid scintillator materials that combine LBC with other scintillating compounds. So these hybrid aim to enhance specific properties such as increasing the detection efficiency for particular types of radiation or improving resistance to environmental factors. This innovation can lead to tailored solutions for specialized applications. Another exciting area is the potential for LBC scintillators in new applications in markets. So, with ongoing advancements in material science and detector technologies, we foresee LBC being utilized in areas like space exploration, high resolution radiation detectors for studying cosmic radiation, protecting astronauts, and ensuring the success of long duration missions. LBC's superior performance characteristics make it an ideal candidate for those harsh and demanding environments. The field of nuclear medicine also poised to benefit significantly from LBC scintillators. So as medical imaging techniques become sophisticated, the need for high resolution, accurate detectors grows. LBC can provide the precision needed for early diagnosis and treatment, improving patient outcomes and advancing healthcare. And moreover, we can also see that the increase on environmental monitoring and safety opens up new markets for LBC based detection systems as regulations and standards for safety become more stringent. So industries will require more reliable and precise detection solutions. So LBC simulators can play a crucial role in ensuring compliance and protecting public health and safety. So again, the more we understand what our customers are doing, whether it's uh, new data, emerging technologies, or new white papers, that will really drive how we offer solutions and how we foresee us really working with some of these industries. Okay, now let's turn our attention to the commercialization and market potential of lanthanum bromochloride scintillators. So the global market is projected to grow significantly in the coming years, driven by some of the applications that we just discussed. So medical imaging, homeland security, nuclear power plants, and environmental monitoring. So, according to recent market research, the demand for high resolution and efficient scintillation materials like lanthanum bromochloride is expected to rise. So, with an estimated compound annual growth rate of over 5% through the next decade. So, one of the primary factors driving this demand is the high need for advanced radiation detection and imaging solutions across various sectors. In healthcare, for instance, the growing adaptation of PET and CT scans is boosting the requirement for high performance scintillators. Very similar, increased investment in security infrastructure and the need for radiation detection in nuclear facilities are propelling the market forward. So for BNC, partnering with Psionics and leveraging their expertise in lanthanum bromochloride scintillators places us in a very strong position. Our very strategic alliance and exclusive partnerships here in the U.S. enable us to offer state-of-the-art solutions that meet evolving needs of our customers. So when it comes to strategies for commercialization and exploring business opportunities, several key approaches can be adopted. So firstly, it's crucial to focus on building strong relationships with key customers in target industries. So this involves engaging with medical institutions, security agencies, and environmental organizations to understand their specific requirements and tailor our products accordingly. Secondly, investing in research and development is vital. Continuous innovation and improvement of our simulator technologies will help us stay ahead of the competition and address emerging market needs. So, by enhancing the performance characteristics of lanthanum bromochloride simulators, we can offer superior solutions that provide tangible benefits to our customers. And thirdly, expanding our market research through effective marketing and distribution strategies is essential. So, this includes leveraging digital marketing platforms, participating in industry conferences, trade shows, and building a robust distribution network to ensure our products are easily accessible to customers worldwide. So, exploring new applications and markets is a promising avenue for growth. As mentioned earlier, fields like space exploration, nuclear medicine, they present a very significant opportunity for lanthanum bromochloride. So, by conducting thorough market research and analysis, we've been able to make a very educated decision and pursue this detector in some of our systems, some of our RIDs, some of our backpacks, some of our isotope identification equipment. So, again, we do have a lot of universities and we do have a lot of companies reach out to us with some new crystals that they think will be the new cesium iodide or sodium iodide. But again, we just want to uh, just clarify that there's a lot that goes into uh, choosing some of these crystals. The competitive landscape and implementing some of these strategies, we can we want to make sure that we're capitalizing on some of these opportunities. We want to make sure that some of these new crystals don't just go away, right? We want to support them. We want to make sure that there's a long lifespan for these new materials. So again, we do our due diligence when we do pursue some of these new materials that aren't your most common. We want your questions. This is the time. You have our Mark Slattery to ask some of these questions that you've been waiting to to get answered. So, top right of the screen, ask those questions.
Thanks everybody for listening. Let's see some of the questions that we've received so far. Uh, Jay Lynn has asked if this company, if the webinar is recorded and shared after the meeting. Yes. In fact, we will be sharing the of this recorded version of this after and to all of the participants. We had another question, which I think maybe was answered. Raymond Clan had asked about the commercially available dimensions for lanthanum bromochloride. I mentioned it's about 2 inches in diameter, 4 inches in length. If you're looking for cuboid type geometry, then limited to maybe about a 36 by 36 square would be the available area. Walter Reviol has asked, what is the price comparison with LBC and lanthanum bromide? It varies depending upon size or geometry of one scintillator or size compared in one material and the other material. Again, the size and shape have a bit to do with that. I'm going on very rough, more like anecdotal information on this. We find that LBC is about maybe 20% higher than cerium bromide. I'm sorry, 10%. Make that about maybe 10% higher than cerium bromide, also very bright and very fast. And we find it to be 5%, and in a lot of cases, maybe even 10% less in cost than lanthanum bromide. So I hope I've been able to answer that question. Let's see what else is coming in here. What is driving the limitation in crystal size, meaning the 2-inch? I would have to get that information from the grower, but for the most part, expense is a part of it. Ensuring quality, that there's no degradation in quality. That becomes a little tougher as we start getting into larger and larger dimensions. So currently, we gave you the commercial availability. There is work going on to making larger dimensions available. And again, the word here is commercially or provided in an industrial scale. So we're having, say, some success, but we would like it to be bulletproof before we can make larger dimensions available. What thickness does LBC come in? And can be made for imaging in a thicker piece. Energy, 100K BE radiography. I'm not that familiar myself in radiography or in measurements, nominal uh, values of that type. The thickness of LBC, again, is it can be, depending upon how you want to cut it or shape it out of the boule, but about 2 inches in diameter, and again, up to 4 inches in length. What thickness? Okay, very, very similar question. Thank you, Laura. Think I think we've worked with you some at Lannel, if that's possibly correct. I sometimes get the names all mixed up. How does LBC compare with lanthanum bromide in terms of efficiency and resolution? It's, I believe, a little denser, and Z, very similar, maybe a little more in efficiency, the ability to absorb high energy. Very, very similar, though, very close. Resolution, for all practical purposes, both of them are 2.8% resolution. Typically, when resolution is presented, a lot of times, the really maximum number is very dependent upon what size of the crystal was used, what was the light detection and electronics that were used, and these are usually achieved in ideal instances, which if it hardly ever turns out that way in the real world, in practical applications. So I'm going with the 2.8 resolution. The two of them are very comparable in that issue. Oh, is it hygroscopic? Yes, I think I made a mention of that. It is hygroscopic. It must be encapsulated and hermetically sealed, handled in, if it's encapsulated, it's got to be handled in argon dry boxes and so forth, technology like that. How stable is photo peak position with temperature over 40 degrees C to 50 degrees C, as well as energy resolution? I'll be honest, I don't know the results. I had mentioned that ESA testing is still ongoing. We are able to do some thermal cycling and evaluation in our own factories. Some of the rest of this, I think, will rely on the samples, the detectors that we've provided for NASA, for other organizations that are probably better suited and have more resources for determining that. I would like to try and gather that information. It's a good question. I will try to follow up on that. Let's see. Maybe
We got Alexandra in there.
what's the
Yeah.
time resolution? Yeah, less than 25 nanosecond decay time. Which is the shortest time interval between pulses can be checked? I don't. Pulses can be. I'm not sure I understand the phrasing of that. If you're talking about, I would say still most of the limitation on the speed at which you can process signals more often than not applies to the PMT or the SIPM that is being used to convert the light into electronics. You can have really ideal scintillation. You do want to have a high Q type of a PMT. high speed PMTs to process that information. And then, of course, the electronics, software, and so forth that you use to use that instrument. Um, yeah, that's going to vary. Uh, I would say, you know, over 100,000, 150,000 counts per second is achievable. Processing up to 400,000 counts is achievable, but again, hardly ever. And this has less to do actually with the decay time of the scintillator than it does with the electronics and light detection that's being used. Um,
I think that's the
what
last
we've got
question we
so
have
far.
in there. But we have a pop-up menu, pop-up that just came in. The best thing to do is, if you are considering some scintillation detectors, is to go to our website. We do have a page that allows you to customize your scintillation detector, and it will ask you very key and important questions about the size, the resolution, if you're looking to use a PMT or SIPM. All these things will really allow us to provide you with the best option forward, because like we just this again, this presentation was specific to lanthanum bromochloride, but there are a lot of other crystals that we work with, sodium iodide, the serum bromide that we just discussed, cesium iodide, and all those have their advantages and disadvantages. That's why it's best to kind of talk to a specialist or go through that sheet and provide us with that information, because with so many moving pieces, there are things that we could kind of pick and choose that will kind of allow us to offer the right solution for you, right?
One of the key, I mean, obviously, what size do you want? Uh, what are the environmental conditions for the detector that you want? One of the key things is let us know what your application is.
Hmm.
As great
Hmm.
a detail as you can. Describe, this is what we are hoping to prove. This is what we're hoping to detect. This is the goal of our application. Our design team at Psionics, they may have solved a similar application already. They really are the experts. They will. Their motto is a good way to put it would be, you know what it is you want to measure, so just tell us what it is, and we will make a detector to help you do that. So you tell us what you're looking for, we'll give you the expertise to achieve that.
Very good. I think that's all the questions we have, Mark.
Well, okay. Thanks, everybody. We appreciate you taking the time out of your day to attend. Alan, do you have any other further words?
No, I think that's it. Like we discussed, this is a very promising crystal that we're going to be offering, and we don't. There's a lot of, like we said, we're going to be attending the IEEE Nuclear Symposium conference this year
Tampa?
in
Is that right?
Tampa, correct?
Okay.
We always hear about the crystal that's going to be the latest and greatest, but we want to make sure that we do our due diligence, and we really test some of these crystals, because we understand that uh, we want to make sure that they work appropriately, pretty much. So, but this is one that we've tested, we've tried, and we do have customers that are using it, and they are getting very good success. Okay.
Very good.
All right. Thank you, everyone.